I wanted to go over with you briefly a term that's thrown around a little bit in chemistry, not always super well defined, so some of these examples may seem a little bit wishy-washy, but now that we're all familiar with buffers and how a buffer is created with a little bit of acid in its conjugate base or base in its conjugate acid, and we're probably also familiar with the Henderson-Hasselbalch equation or even simply the Ka expression. If I had a little bit of, not a little bit, if I had a sizable amount of A minus from, say, sodium A minus, potassium A minus, lithium salt of A minus, and its conjugate acid, excuse me, HA, then I can use that relative amounts of A minus and HA to describe something we call buffered capacity or buffering capacity, or the capacity of a buffered solution, a buffering solution to neutralize incident acid or base. Here's an example that we might see somewhere else on a different video or different topic, but I can use it. If I had 20 grams of NH3 dissolved in the same water as I had 50 grams of ammonium chloride, change grams to moles, and I have 1.18 moles of NH3 and 0.935 moles of NH4 plus ammonium in the same beaker of water. That serves as a buffer. This is the conjugate acid of this weak base, and I can pull out the Henderson-Hasselbalch equation in the basic buffering form to figure out the pOH and find out the pH. But in any case, I put the see, this is bases, so I put the base on the bottom and the acid on the top. But you don't have to remember that. You're given the Henderson-Hasselbalch equation. But I'm saying this buffer with the pH of 9.36, that should be an equal sign, 9.36, can consume or could neutralize 0.935 moles of base that come into it, or 1.18 moles of acid, because the acid would neutralize the base, or the base would neutralize any incident acid, or the acid would neutralize any base, or the base would neutralize any acid that might be accidentally or on purpose introduced into the system. So if this 0.935 moles is reflective of the conjugate acid or the ammonium ion acidic part of the buffer, then the capacity for this buffer for neutralizing base would be to the extent of 0.935 moles. And by similar reasoning, 1.18 moles of NH3 could neutralize 1.18 moles of any acid that might come into the system. I don't know if the word neutralize is proper. It would react with. If I had OCl minus, a weak base molecule in the water, I added to it a strong acid, 50 millimoles of strong acid, to 50 millimoles of weak base ion, they would react in a 1-to-1 ratio, and indeed I would create, I see the question. Here I have 150 millimoles of weak acid and 110 millimoles of its conjugate base. If I were to introduce into this system with a partial titration, so I add some H plus to the system, well, the H plus reacts with this and brings it down a little bit, and in so doing the H plus attracts the OCl minus, creating more HOCl. So this one goes up by 50 millimoles, this one goes down by 50 millimoles. Well, the buffering capacity could just be described as 110 millimoles of OCl minus able to neutralize 110 millimoles of H plus. And the HOCl, 150 millimoles, could neutralize 150 millimoles of random excess stray base that might enter into the system. But now I've changed the buffering capacity a little bit by reducing this by 50 millimoles and increasing this by 50 millimoles. Now I suppose I could think about the system as having a greater buffering capacity for the base because I have more acid, and a lesser diminished buffering capacity for the acid because I have less of that conjugate base. But in any case, this is, of course, from a previous video how we'd find the pH. But more importantly to the topic here, what's the buffering capacity of this buffer? Well, if I have 60 millimoles of conjugate base, it can only neutralize 60 millimoles of acid that might enter into the system. But if I had 200 millimoles of weak acid, then it could neutralize 200-ish millimoles of strong base that might enter into the system. Interesting. Here's a buffered solution with, oh wait, that's what? This slow, my goodness. Maybe I should reorder this. Oh no, it's the same buffering system, HOCl and OCl minus, starting at the same place, 110 millimoles and 150 millimoles. But if I introduce some OH minus to the system in a partial titration, what would the OH minus react with? It's a strong base, so it would react with this acid. What's 27.5 times 1.2? Oh, it's 33 millimoles. So if I introduced instead 33 millimoles of strong base, it would diminish this acid by 33 millimoles, reducing this to 117 millimoles, increasing this to 143 millimoles. Then my buffering capacity, my buffer has a different pH, slightly different pH, and my buffering capacity is changed again. Now I can neutralize 0.143 millimoles or moles of acid that might enter into the system because it would react with the conjugate base here, conjugate base in the system. Or I could neutralize 0.117 moles of base that might react with this HOCl. When you first hear about this, I'm not sure it makes a lot of sense. You're going to have to go digest this and think about it and struggle with it a little bit. To maximize the buffering capacity, usually we say, let's have equal amounts, the same amount of acid and conjugate base. Like if I can dissolve 1 mole of acid and 1 mole of its conjugate base into the same beaker, then I have a buffering capacity of 1 mole. I could say it that way anyway. 1 mole of acid or 1 mole of base could be neutralized by that 1 mole of 1 mole of each in the buffering system. Buffered system is created by 0.23 moles of acetic acid and 0.19 moles of lithium acetate. Lithium acetate, so this acetate ion is the conjugate base of this acetic acid. I think I have in my mind how I would set up the Henderson-Hasselbalch equation. Oh, but then, so they set up a 0.23 moles of acid and 0.23 moles of conjugate base. Cool. I guess we could say at that point, before I add this junk, my buffering capacity is 0.23 moles. I could consume 0.23 moles of H plus that might enter into the water with this thing, or I could neutralize 0.23 moles of OH minus that might enter into the buffer with this thing. But then if I adjust it a little bit by adding some OH minus, 0.23 moles of this reacts with all the 0.23 moles of this to create 2.23 more moles of this. So I've created 0.23, what am I saying here? I think I've said that wrong here. 0.23 moles of acetate ion is created. It would add to the already present 0.19 moles. Okay. So in my question up here, I had 0.19 moles of lithium acetate. There we go, 0.19 moles of this. And if I add 0.23 moles, this is coming out terribly, sorry. 0.23 moles of acetic acid. Lord, I need some stimulant of some kind. My brain is falling asleep. 0.23 moles of acetic acid, and I'm going to add what quantity in moles of NaOH would basically overwhelm the buffer. So here's the acid. How do I overwhelm the acid? By adding strong base. In so doing, I would neutralize the buffer, kind of ruin the buffer. I would create then, it would be 0.23 moles of this new acetate ion added to the already existing 0.19 moles of acetate ion from the lithium acetate. Then I'd have to go back. I don't think if I did it here. I'd have to go back and say, what's 0.23 plus the already existing 0.19? That would be 0.42 moles of A minus in the water. We could do a calculation from there to figure out what the new pH would be. But in any case, remember, don't you, that the strong acid being titrated with a weak base, a strong acid with a strong base has a very flat-ish pH in the beginning of the titration. And so remember, this is not a buffer. But remember also, that if you have a weak acid titrated with a strong base, then the but anywhere before the equivalence point can be considered a buffer. Because if I add only a little OH minus, say to here, I have still quite a bit of acid in the solution, but I've also created the conjugate base, or some of the conjugate base. I think this might be a topic of a different video. It is. Or if I go to here, I've created 30 relative units of conjugate base, but I still have 20 relative units of the weak acid HC2HCO2 remaining in solution. So here, anywhere along this line, we have a mixture of the original acid, some of the original acid, and some of its conjugate base created by the partial titration. Yeesh, are you looking forward to that video on partial titrations of... No, you're not looking forward to any video. You're looking forward to this semester being over, eh? Yeah, we'll get there. Thanks, guys, and I'll see you in class.